The next problem is a beam with a uniformly distributed load, a simply supported beam. So as you see over here, you have a simply supported beam on top of which you have this uniformly distributed load. Maybe we call this load as, say, W. So it is W per unit length which is acting over here. Now for this beam we will derive the shear force and the bending moment diagram, and as we did previously, let's just draw two of the same beam. On one of them I'm going to draw the shear force diagram, and on the other one the bending moment diagram, right? Okay, now if you take a look at this beam, it is a very symmetric kind of a structure, and that first of all it tells you that Ra is going to be equals to the total load acting on the beam is going to be a product of W times L. So the Ra will be equals to WL over 2, and RV will be equals to WL over 2 over here. Right now, if you take a look at this beam, there are no discontinuities which are caused by any point loads acting in between. It's a beautiful symmetric structure where you have a load W throughout, so it doesn't really matter where you take the section along the length of the beam, right, to derive your shear force diagram and the bending moment diagram. So if we go ahead and maybe take a section anywhere at say a distance x from the left to the right, which is marked over here, and if I draw this part of the beam and try to write the equilibrium equations, what I get. So let's just go ahead and draw the beam again up to this particular point where here at the left end I have the reaction Ra, that is WL over 2, right? I have this uniformly distributed load that is acting. This is my small w that is acting over here, and at the right end where I have cut this section, that section is at a distance x. So what I have over here is that from here to where I have cut this section, this one is at a distance x over here. So now if I am going to mark my shear force and the bending moment, since I am going from my left to the right, always remember the positive convention for the shear force is that I'm trying to rotate the beam in a clockwise manner. So this is going to be my V, right? And I'm trying to bend my beam into a trough or sagging. So this is my M. Again, I'm repeating this multiple number of times. This is the positive convention which you drew. When you solve the problem, when you try to work it out, these signs will take care of it themselves. So this is what you have initially marked based on your positive convention. The problem might tell you that V is negative, M is negative, and so on. So for this one, if we now try to write the equilibrium equation, so what we have over here is that so for V, so let's just try to write the equation for V. So what I get is that I have this reaction RWL over 2 over here, and as a consequence of this load W, this may be represented by one single equivalent load. So let me go ahead and mark that one. So if this is W acting over a distance x over here, so the equivalent for W can be marked at a distance of x over 2, and what is going to be the magnitude of that one. So let me go ahead and maybe mark that with a sort of a squiggly line. Right, so this one is going to be your W times x. So that is the total equivalent load which is acting over there. So now for the V, if I have to write the equilibrium equation, what I have is that V minus RA plus Wx will be equals to 0. So if I go ahead and simplify this a little further and I put the value of Ra, is going to be W L over 2 minus Wx. So how does the shear force vary? Let's see. When x equals to 0, V is equals to WL over 2, which is obvious because at the left end you have the shear, because of this reaction you have a shear force point. So you don't essentially have any option but to have a WL over 2 over here. So let's maybe write from here. So at x equals to 0, what we get as V will be equals to WL over 2, which means if I have to go ahead and draw in this shear force diagram, what I get over here is I have a vertical line which goes up, which is a positive WL over 2. So this, the first diagram is the SFT. So I'm drawing the shear force diagram over here, right? Now you see that this is a decreasing function over here. So WL over 2 minus X, right? So what happens at, and it's a linearly decreasing function that you have. So what happens when X goes from 0 all the way to the length L? So let's try to write that as well. So at X equals to L, what you get? V. Can you guess what you will get? Of course you will get a negative WL over 2, because then this reaction is pushing it up over here. So you get a V equals to minus WL over 2. If you put L equals to here, WL over 2 minus WL is minus WL over 2. So here at the right end I have minus WL over 2 over here, right? And in between, as you can understand, that it's a linearly decreasing function. So somewhere along the line it will be, you know, it will cross the 0 point. And can you guess where? Yes, from the symmetry of the structure you can easily guess it is going to happen at L over 2, or otherwise you can, you know, do the differentiation and you can calculate where this, or not the differentiation, you can just equate this to 0 and you can find that at what X. So if you equate this to 0, you have WL over 2 equals to WX, so X becomes equals to L over 2. So let's also mark that at X equals to L over 2 you get V equals to 0. So how is the shear force diagram going to vary? The shear force diagram is simply going to vary something like this, right? So you have a positive part and a negative part over here. Okay, so that is how the shear force diagram is going to vary. Now let's come and take a look at the bending moment diagram. So if I have to write the expression for M over here, what do I get? So for M, if I have to write for, I'm calculating, if I take the moment of the forces about this particular point, I will get M plus, due to this load, the magnitude of the load is Wx and it acts at a distance of, you know, X over 2 over here. So this particular distance at where it acts is X over 2, right? So Wx times X over 2 minus WL X over 2 equals to 0. If I have to simplify that expression, M becomes equals to WLX over 2 minus WX square over 2. Again, even before we plug in the numbers and everything and try to find that at X equals to 0, so as you see in this beam, you have the left end and the right end. You have at the left end you have a pin, and the right end you have a roller. Now as you can understand that when we have these pins and the rollers at the extreme ends of the beam, and at those points if there is no externally applied moment, the value of the bending moment will be 0, which you can see here as well. So here if you put at X equals to 0, then your M will become equals to 0. If you put X equals to L, it will be WL square by 2 minus WL square by 2, so that becomes equals to 0 over here, right? Now in between these 2 points you will have a variation, and as you can see from the figure that you are going to have a quadratic kind of a variation. So the bending moment varies in a quadratic kind of a way, right? And where does the peak happen? Where does the maximum bending moment happen? To find the maximum, you can simply take the derivative. So I get that dm dx will be equal to WL over 2 minus Wx, right? So if I equate that to 0, that will give me at X equals to L over 2, I am going to have the maximum moment is going to happen over there, right? And what is going to be the magnitude of that moment? So to find the magnitude, I'm going to put X equals to L over 2 over here. So what I get, M max is going to be WL over 2 times, now I've calculated the X as L over 2 minus W by 2 L over 2 square. If you solve it, I remember it from the top of my head, you will too once you solve several bending moment and shear force diagram, you get a WL square over 8, Okay. So what did we just derive from this entire thing which we just wrote down over here, that the bending moment is 0 at the left end, is 0 at the right end over here, at 0 at this pin and 0 at the roller. It has a quadratic variation which is going. So let's just maybe write that down. So it has a quadratic variation, right? So it has a quadratic variation, and the peak happens at x equals to L over 2, and the value of the peak which we just calculated is WL square over A, right? So if I have to this, so this is the distance where you have, so this is L over 2 over here. So if I have to go and draw my bending moment diagram, it somehow varies something like this over here. And remember that the entire thing is positive. The value of the moment that you got is positive, so the positive is drawn in the upward half and the negative in the bottom half over here. So for the bending moment diagram at this exact L over 2 distance, I get the maximum value as W L square by 8, right? And this entire diagram is positive. Right. So as you saw, for a beam with a uniformly distributed load, this is how the shear force varies over here, and this is how the bending moment varies. Now a couple of things which are takeaways which you should always note while solving these problems, that and which you will see intuitively makes a lot of sense as we progress in through the lectures in this topic. You see, the maximum bending moment happens where the shear force is 0. So just make a note of that, why it happens and the reasoning behind that, and in what other cases similar situations arise. We'll take a look in one of the upcoming lecture topics, but just for the timing, just make a note. Also go back to your intuitive principles, that here, since it's a pin and here you have a roller at the two ends, no externally applied moment, so here you're going to have the bending moment 0 as well. So I hope this particular problem example was clear. Let's move on to the next one.